Hello everyone, and welcome to this month's webinar on sample size and power for non-parametric analysis. In this webinar, we will cover non-parametric tests, some non-parametric equivalents to popular parametric tests, and then we will also look at a couple of practical examples of sample size determination for a selection of non-parametric methods in inquiry as well. But before we get to that, I'm just going to run through a few quick bits of housekeeping first. So today's webinar brought to you by Enquiry is being recorded, and this recording, along with the slides used and the example files, will be sent to you shortly after we conclude here today. If you have any questions, feel free to type those in the chat box, and I will do my best to leave some time at the end for them. However, if we do run into time constraints, I will be sure to answer any of the questions via email as soon as is possible. The same goes for any questions that you may have after this webinar has concluded. I will answer those via email as well. You can also use this chat box to inform us if you experience any technical difficulties, and one of my colleagues will do their best to resolve them for you as quickly as possible. So before we go any further, just by way of a quick introduction, my name is Dennis Desmond, and I am a research statistician here at StatSolves, and I will be your host for this webinar brought to you by Enquiry. Also, I'd just like to start by saying thank you all for taking the time to join us today. So just to give a very quick rundown of the agenda for this webinar. Firstly, we will start by talking about parametric assumptions, just to set the scene for this webinar. Then we will move on to talk about some non-parametric methods before we move on then to take a look at sample size methods for non-parametric tests. And at this stage, we will take a look at some worked examples in inquiry as well. Finally, we can wrap things up with some discussion and conclusions, and of course, time allowing, we will get to the questions that may come in from the chat box along the way as well. So, as I mentioned, this webinar is brought to you by Enquiry, the complete solution for optimizing your clinical trial designs from preclinical research through to post-marketing studies, with the main focus being on confirmatory phase 3 trials. Enquiry features over 1,000 scenarios for fixed-term, Bayesian, and adaptive studies. So Enquiry is very widely used in the pharmaceutical and biotechnology industries, with 88% of organizations with clinical trials approved by the FDA having an Enquiry license. Also, you can see here a number of reviews from some of our customers. If you wish, you can get a free trial of Enquiry from our website, and there will be more on that at the end, including some contact details if you would like to get in touch with us and get any further information. So with that, I think we have all of the housekeeping and introductory items covered. So we are good to get into the content of today's webinar. And as I mentioned, firstly, we're just going to give a brief introduction to parametric assumptions. So statistical methods have assumptions in order for their interpretation to be statistically valid, and all methods will have some kind of assumptions, but they will fall into different types. And so in today's webinar, we are going to be talking specifically about parametric assumptions. So these are assumptions about the underlying distribution and about the form of the data. And so by the form, I mean, like, is it continuous, ordinal, etc. So One common example of a parametric assumption is the normality assumption used for t-tests and ANOVA type methods. Alternatively, you can think of a parametric model as being one that is defined using a finite set of distributional parameters. And then in the case of non-parametric models, this need not necessarily be the case. And so a lot of clinical, real clinical data does not map onto these parametric assumptions. So the most notable of which would be complex continuous data. So that's data with extreme outliers, ordinal data, or interval type data. Now, I should note as well that parametric tests do often hold up well, even in the presence of distributional divergence. So just to use the example from above, the t-test is actually quite robust to deviations from the assumption of normality. And it's generally in the case of extreme outliers, like I said, which is where you'd need to use an appropriate non-parametric test. With that being said, though, these types of flexible statistical methods can be exceptionally useful tools for handling these trial scenarios. And so that's what we're going to cover today. So this next slide is just taking a look at parametric versus semi and non-parametric methods. And as we mentioned on the previous slide, parametric methods are those that make distributional assumptions about the data generating process. And we've already mentioned a couple of these examples, but you can see them listed here. And there's also linear regression, generalized linear models as well. But then on the other hand, semi-parametric methods have both a parametric and a non-parametric component. So often there will be a parametric linear or additive component of interest with the underlying distribution left undefined. So in the case of the Cox regression model, there are assumptions made for the hazard ratio, but the distribution of the underlying data does not need to be specified. Now, another example of a semi-parametric model would be the proportional odds model for ordinal data. Now, finally, methods which make no or minimal distributional assumptions about the data generating process are non-parametric. And so in reality, there are very few statistical methods which make no distributional assumptions. So that's why we have the caveat of minimal distributional assumptions in brackets there. So some examples of these would be the Wilcox and Mann-Whitney U test, Wilcoxon's rank test, and those will feature in our worked examples later. And then there's also Kruskal-Wallis and quantile regression. So now we're going to move on to some non-parametric methods. And as we just mentioned, non-parametric methods make no or minimal distributional assumptions about the data. So the word of caution about this, though, is that the fewer assumptions can come at the cost of interpretability and a lower statistical power. So it's natural that when you're giving up information that there will be a loss of efficiency. But with that being said, if you were to use a t-test, say, and the required assumptions weren't met, then there would be an even greater loss of power. Now, there's a blog post from Frank Harrell in the references at the end of this slide deck. And he puts forward that non-parametric tests are often the equivalent of a subset of a semi-parametric model under certain conditions. So for example, if there are no covariates present, and some of the examples that he goes through in that blog post are that a log rank test is a subset of Cox regression model, and Wilcoxon tests are a subset of the proportional odds model. Now, any further detail on this is a little bit beyond the scope of the webinar today, but as I said, that blog post will be linked in the references down below. So these types of methods are highly useful for dealing with complex continuous data, where there might be extreme outliers or infinite variance, and also ordered data as well. So be that ordinal or interval type data. So traditionally, non-parametric methods have been more associated with testing rather than estimation, but non-parametric regression models like quantile regression are growing in popularity. For this webinar, though, we are going to focus on non-parametric rank tests and their associated sample size and power. So, rank tests are a common type of non-parametric test used for complex continuous, ordinal, and interval data. Rank tests are interested in the hypothesis, or in hypothesis tests based on relative ranks of outcomes for each subject across groups, and not the underlying value. So the hypotheses are framed around the probability of X greater than Y type statistics. So for example, in the Wilcoxon Mann-Whitney test, ranking is done on the combined data, and it is testing whether observations in one group tend to be larger than that of the other. So this is the general case anyway. The exact definition can be more complex in some instances, and especially in the presence of ties. But for the purposes of this webinar, we are going to be using the probability of X greater than Y definition. So rank tests are often conflated with tests of medians, but this misconception is only true under the assumption that the distributions are identical, just with the median shifted. And then many of these rank tests can be mapped onto an equivalent parametric test. So an example would be the Wilcoxon Mann-Whitney U test being equivalent to the t-test, but we're going to see more about that in a second. So like anything, rank tests have their weaknesses, and so they will tend to struggle with estimation in things like confidence intervals, and also for data dependency for covariates. So in these scenarios, you may wish to consider a semi-parametric model. And as we mentioned on the previous slide, the proportional odds model is a good candidate for ordinal and interval type data. So next, we're just going to look at a couple of non-parametric tests, and this is just a simple slide to illustrate some of the examples of some common mappings. So in the left-hand column, you have some common parametric tests, and then on the right, there are the non-parametric equivalents. So if you are concerned about extreme outliers or some of the others assumptions not being met, then for the one sample or pair t-test, you can use the Wilcoxon signed rank test. For a two sample t-test, you can use the Wilcoxon Mann-Whitney test. And then for ANOVA, you can use either the Kruskal-Wallis or the Friedman approaches. So in the last column there, you can see that for Pearson's, if you aren't sure about the requirement for the assumption of normality or for a linear relationship, you can use Spearman's correlation here. Lastly, then down the bottom, we have some other alternative non-parametric tests, such as log rank tests, non-parametric regression, Cohen's kappa, etc. So now we're going to move on to sample size for non-parametric tests. And so different approaches are required for continuous and ordinal power analysis, even if you are using the same power formula. The practical input requirements will be different. So for continuous data, you can specify the first moment P1 directly, but usually you will need to specify a data distribution regardless. So I know we're using non-parametric tests, so it seems a bit counterintuitive, but it can be hard to work out these moments pre-trial. So it is often expected that you will make a distributional assumption in order to calculate these moments. Alternatively, you could use the exemplary data set approach that is mentioned below. And by doing so, you can create sort of an empirical distribution. So we'll be seeing something kind of similar to that in one of our examples in a moment as well. Now, most common power methods will also assume the location shift hypothesis. So in other words, that they're the same distribution under the null and alternative, but shifted. Then for ordinal data, you will need to specify the proportion of the subjects in each rank across each of the groups as well. And then listed down below, you have some of the power methods for continuous and ordinal data. And so for continuous here, we have the asymptotic relative efficiency, which is a measure of efficiency for comparing the t-tests to the Wilcoxon test, for example. So it is, in other words, the number of subjects required to achieve the same power between the two tests. And so you can use this approach to approximate the sample size for a Wilcoxon test from a standard t-test. The other examples there are the calculation of moments, and that's available for both continuous and ordinal. In the case of the ordinal, you can use methods like Colassa or O'Brien and Costello. Again, the exemplary data set approach and simulation-based power are options for both continuous and ordinal as well. And then for continuous, you have the calculation of moments or the direct input of the moments, like we spoke about just a second ago. So with that said now, we can move on to our first worked example of the day. And this example comes from a placebo-controlled double-blind study of mesoglycan in the treatment of chronic ulcers. So this was a study conducted in Italy a number of years ago, and patients were randomized to either a placebo group or the treatment group, and then the healing progression of these ulcers was monitored over the course of 24 weeks. And you can see here that we have a little excerpt from the paper here with the relevant information for us to replicate this example. And so because There were frequent check-ins required. They recruited approximately 90 patients in each group to account for the dropout, as they found that they would need 70 subjects per group to achieve the target sample, or the target power, excuse me, of 80%, using a significance level of 0.05. And they also assumed a mean time to healing of 84 days in the placebo group, 63 days in the group receiving mesoglycan. They also assumed a common standard deviation of 42 days, and you can see just a tabular summary of that here on the right. So with all that laid out, we can move across to inquiry for the first time today. And just for those of you that may not have joined the webinar before, I'll just quickly run through a few points about inquiry. So if you wish to open a new table, you can do so from the File New menu, or you can do so by clicking on this spreadsheet icon here, or also by clicking Create New Table on the home page. You have a number of radio buttons here which you can use to filter down the available tables, and also you have a text box here to search directly. On the tables themselves, on the left hand side here, you have the row names detailing the inputs required, and each column serves as an independent calculation. On the right hand side here, as we progress through, you'll see that there will be some help cards giving more information about the variables required, and also if you click the home icon up here, you can get to the references for the particular calculation as well. So last thing I will just say is that calculations will automatically run once there have been enough values provided, but you can also choose from down below here in this drop down which calculation you'd like to run. So with all that done now, that should be enough to follow along with our example, and we can start by filling in our values here, which is 0.05 for our test significance level. Now this drop down here allows us to choose a one or a two-sided test, excuse me, but in this case we're going to keep it at 2. Now once we click here into the cell for P1, we can see that this side table opens up down below. So in inquiry, side tables are a method to provide extra information in order to calculate a cell in the main table up above. So in this particular case, we could specify P1 directly, but we are going to use the group means and the standard deviation that was provided to us. So we are going to fill in here the values that we got from the example. And so you can see here that the difference in means is automatically calculated. We fill in the common standard deviation. And for some of the side tables in inquiry, once you've entered enough information down below, you'll need to click this compute button in order to calculate the effect size and P1, and then this transfer button in order to send this value for P1 up to the main table here. Now all that's left for us to do is enter in our sample size per group of 70, and you can see that we got out our 80% target power. So I'm just going to click over here to the t-test for 2 means, because I mentioned the asymptotic relative efficiency earlier. And so for a t-test compared to a Wilcoxon based on normal data, the asymptotic relative efficiency is 3 over pi, which works out to about 95%. So if we fill in these values here into the t-test for two means, we can just take a look at that. And it was 80.83% power. So if we go up to the Windows, or the Assistance menu, sorry, and we open the Windows calculator, we can just do 3 divided by pi, and we can see here that 95.5% roughly is the relative efficiency of the Wilcoxon test compared to the t-test in the case where the assumptions of normality, etc., hold. So if in this case we do 66 divided by 70, and you can see it's about 94%. So relatively speaking, this sample size is quite low. So if we just minimize that for a second and just in the second column here, generate a toy example where we just increase the standard deviation in order to increase our sample size, we can just see that as sample size increases, we will have the efficiency, or the that percentage tend towards the relative efficiency for the test. Excuse me, sorry, I'm after making a mess here. So 200, compute and transfer. And so if we want to target 80% power, we're going to get 1494, and excuse me, never filled in 80% here, 1425. So again, if we just fill in you can see here 95.38. So as n increases, this number is going to tend towards that 95.5, which is the relative efficiency of the Wilcoxon test compared to the t-test. Okay, so with that, we can move back over to the slides and just take a look now at our second example. And so this comes from a study on functional electric stimulation of the ankle dorsiflexor in children with hemiplegic cerebral palsy. So once again, we have a summary from the paper of the relevant information for this example. And in this study, they had a target power of 80% with a one-sided test significance level of 0.05 and an effect size of 0.8, which in this case is the median difference divided by the standard deviation. So they found that they would need a sample size of between 11 and 14 patients to achieve their target power, depending on the distribution used in the calculation. So either a Laplace distribution or a uniform distribution, and we can take a look at that in a moment. And so after dropout, their final sample study comprised of 15 patients per group. So what we're going to do now is we're going to move back over into inquiry, and we're going to open up the table for the Wilcoxon signed rank test. And to start off again, we are going to fill in our test significance level of 0.05. This time we're going to change this drop down to 1. Now this row here allows for a continuity correction. So as you can see just from the help here on the right hand side, that's an adjustment that is made when the discrete distribution is being approximated by a continuous one. So we're going to leave that off for now. And what is going to happen is we're going to click in here to the first moment, and once again we are going to get a side table open up down here, and excuse me, sorry, the gear icon here just above this side table, you can see that it actually offers a couple of different options for us. So first option is to calculate the moments using the effect size. So these 4 moments here are going to be calculated from this side table down below. So there's one for the effect size. Then you can see that we can calculate the moments using the unstandardized first moment, or lastly, we can calculate the moments from pilot study data. So this is kind of akin to that exemplary data set method that I mentioned earlier, where if you do have a pilot study available, you can enter in the size of that study, and then for each of the subjects, you can enter in either the first and second condition value, and the difference will auto-calculate, or you can just enter in the difference, and from there we can use this set of subjects to compute the moments required for this calculation. But we're going to use the effect size version, just as that was what was provided in the study protocol for this trial. So you can see here we have this distribution option, which is a drop-down, which allows us to choose one of 4 distributions. And as you saw in the excerpt from the paper, they used the Laplace and the uniform. So for the first calculation, we're just going to click on Laplace, and we're going to enter in our effect size of 0.8, and then we can use the compute button again to calculate our moments. We'll then hit transfer and send those up to the main table. So the next thing that we're going to do then is we're going to put in our target power of 80%, and you can see that we get the number of pairs to be 11. So that was for Laplace. If we then enter in the values again, and we get a new instance of the side table. And so I'll just quickly take this moment to have an aside to just quickly talk about the side table convention in inquiry. So you can see here that there's tabs down the bottom. There's MOT8, which is this table S1. So this is the first side table, and this is the second side table. And so each of these numbered columns will refer to the numbered tables will refer to the numbered columns up above. So the moments for the calculation in column 2 will come from the side table 2 down below. So we will now click uniform, and again we'll pop in our effect size, and we'll hit compute and then transfer, and again we're looking for a target power of 80%, and again you can see we got that 14 back. So nice and simple, and with that then we can pop back to the slides and we can move on to our final example for the day. And this is a 2-sample ordinal case from a study into prehabilitation of elderly, frail, or pre-frail patients prior to elective surgery. So frailty is expressed in this setting by a reduction in physical capacity, mobility, muscle strength, and endurance. And this leads to an increased risk of complications surrounding surgery. As such, these patients are at risk of being limited in their recovery. They can suffer a decrease in their quality of life, or sometimes a decrease in functional and cognitive capacity as well. So the goal of this study was to see if prehabilitation before surgery could reduce a patient's care dependency in the 12 months post-surgery. And here in this case, prehabilitation intervention involved exercise therapy, balance training, and things like that. So they found that 470 patients in each group will have 80% power to detect the expected quantified effects shown in this table here using a Wilcox and Mann-Whitney rank sum test with a 0.05 two-sided level. So with that, we can go over to inquiry one final time today, and we can open up the table for the Wilcox and Mann-Whitney rank sum test for ordered categories. So we're going to start as usual by filling in our significance level of alpha, and it was a two-sided test, so we're going to leave that as it is. And then we had 4 categories. So what this does is this opens up again another side table down below, and this will allow us to input the proportion in each of the categories for each of the groups. So you can see here in this case that P1 cell is gray. So in inquiry, gray cells are read-only cells, and so in this case we don't have the option to directly specify P1. We're going to have to use this side table down below. So let me just start off by putting in the control proportions. Okay, and then the treatment proportions. Okay, and then we can hit compute here and we can get out P1, and we can hit transfer and that goes up there. Now, they found 470 patients per group achieved their target power, so we'll pop in 470 and we'll see that we get out 80.09%. So just quickly to note as well before we finish up that that Frank Harrell blog post that mentioned that that the proportional odds model was actually the Wilcoxon test was just a subset of proportional odds model. So what we can do here is, because of the assumption of proportional odds, we can't replicate this example exactly in this table for proportional odds. But what we can do is we can create a toy example where we enter in the same values for treatment. Excuse me, sorry, I'm just going to quickly fill these in. And what we can do is we can pop these values back into a new instance of the Wilcox and Mann-Whitney test. And so these will be the same as before. But what we will use for the control proportions will be the proportions from this group here. So that will be and then the last one was 0.035. And so if we compute and transfer, and again we put in, so you can see here that obviously the power isn't exact, there'd be, there are two different methods and rounding, but that in the case where the proportional odds hold, that the Wilcoxon rank sum test can be seen as a subset of this proportional odds model. So just an interesting little aside from Frank Harrell there, and just wanted to point that out, just with that little toy example there. So on that note, we're going to move back to our slides here and begin to finish up. So we saw today that many common statistical methods require making assumptions about the underlying data generating processes. So these are the parametric assumptions, but that when these assumptions are not met, be that for extreme outliers or the data being ordinal, then the more flexible semi and non-parametric methods are more appropriate. Non-parametric methods make no assumptions about the underlying distribution, and rank tests are a common approach for testing in the presence of complex data. Lastly, we saw that power and sample size methods for non-parametric tests are available, but that they typically require specifying the distribution or an ordinal data frequency pattern, which again is slightly counterintuitive, but we covered the necessity for the calculation of moments just there, so that's an assumption that we needed to make. So I'm just going to have a quick look across here for your questions. So yeah, there's one here that we kind of just covered, but in the Wilcoxon sign rank test example, you needed to select a distribution. Is this a semi-parametric test? So yeah, that's a good question. Thank you. So it is classed, we just touched on there, it obviously classed as a non-parametric test, as it, it doesn't require the assumptions about the underlying data, but we do have this necessity just to specify distribution in order to calculate the moments. So yeah, and again in that blog post from Frank Harrell that I mentioned, I think that he does actually argue that the label non-parametric is oftentimes a bit misleading, and he does make kind of a strong case for these tests being considered as special cases of semi-parametric models. So good question. Yeah, thank you. And yeah, it is one like that can be slightly counterintuitive. So with that, I think we can start wrapping up. And if any further questions come in, I can take those via email. So if you don't already have a license for inquiry, or you would like to try it out, you can go to statsodds.com/trial to get a free 14-day trial with no download or install required. It can be accessed through your browser, and there are no credit card requirements either. You just need to provide an email address. The trial will give you the latest version of the software, and in addition, it will give you access to all of the available tiers. So that's base, plus, pro, and expert. So you'll be able to try out tables for fixed term, adaptive designs, and prediction as well. So if you have any questions, you can email them to info@statsols.com, and myself or one of my colleagues will get back to you. We'll make sure that, depending on what your question pertains to, we'll put you in touch with the best person suited to help you out. Also, feel free to reach out to us if you have any feedback about these webinars. We love to hear from you, or if there's an area you'd like more detail on, or a topic that you'd like to see featured in a future webinar. We love to hear those suggestions, so please do reach out. And speaking of the webinars, there is more information and additional content, including the full library of our past webinars on a wide range of topics, available on our website, which again is statsols.com. And then also at the end of the slides here, you can just see that I've provided a list of references. And just to remind you that these slides, along with the recording of the webinar itself and the save files containing the examples used in inquiry, will be sent out to you shortly. And again, if you have any questions about any of that, please do reach out, get in touch, and we'll be happy to help. So with all that said, that's all for today. And just before I go, I'd like to once again thank you all so much for your time and your interest in these webinars. And I'll remind you that we do host a new webinar every month. And so we hope that you will join us again soon. So thanks very much again, and until next time, all the best.